Every equation physics owns breaks down at the same point, the beginning. 7 serious attempts have tried to explain what came before it, or whether before ever meant anything at all. Not because scientists agree on which is correct, but because the closest they've come is stranger than the question itself. There's a point, just past 13.8 billion years back, where the phrase "before the universe" stops meaning what it seems to, proved mathematically between 1965 and 1970, almost never mentioned alongside the Big Bang. The observable universe already reaches 93 billion light-years across. The oldest light inside it dates back to 380,000 years after the beginning. And the calculations, pushed back far enough, all return exactly the same number: 0. Here's where tonight goes. We'll examine why a physicist in Indiana thinks you're living, right now, inside a black hole. We'll follow Alexander Vilenkin's equation for a universe that tunnels into existence from nothing at all. We'll sit inside an idea from Stephen Hawking that erases the word "before" completely, replacing it with a shape that has no edge. By the end of tonight, you'll understand exactly why the most honest answer physics has found might not be an answer at all. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. Picture walking backward through the history of everything. Galaxies uncluster. Stars go dark and fold back into gas. Atoms lose their electrons, one at a time, until there is nothing left but a hot, dense plasma with nowhere to hide. You can do this all the way back, 13 billion years and change. And for most of that walk, the physics holds together the way it always has. Then, close enough to the beginning that ordinary numbers stop meaning anything, you hit something that is not quite a wall and not quite a fog. Physicists call it the Planck epoch. It lasts for roughly a 10-million-trillion-trillion-trillionth of a second, and it is not a measurement in the way a stopwatch measures a race. It is the point where general relativity, the theory that explains gravity, galaxies, and the curve of space itself, and quantum mechanics, the theory that explains atoms, particles, and everything smaller, stop agreeing with each other. Push the equations past that point and they do not go quiet. They break into infinities that no instrument has ever recorded, and no calculation can tame. Could a universe really tunnel into existence from a state with no space or time at all, the way a particle slips through a wall it has no business crossing? Once inflation starts somewhere, does it ever actually stop everywhere? What happens to the question before if time itself turns out to have no edge left to stand on? Is the far future of one universe secretly the beginning of the next one, wearing different clothes? Somewhere in a black hole sitting at the center of a galaxy overhead, right now, is an entire new universe already being born? And if none of that settles it, could the honest answer simply be that 10 followed by 500 zeros of universes are all equally real, and this is only the one that happened to end up capable of asking? Here's what almost nobody considers. The Big Bang, as most people learn it in school, was never actually a moment. It is a gap with a label on it. Popular science calls the label the beginning of the universe, and then, politely, changes the subject. The equations return infinity. That single sentence is the reason cosmologists argue about the beginning more than they argue about almost anything else in physics. It is not that scientists are being evasive. It is that the two most successful theories human beings have ever built, tested across a century of experiments and 1 trillion confirmations between them, simply refuse to speak to each other at the one moment you most need them to. Proved mathematically by Stephen Hawking and Roger Penrose in a series of papers between 1965 and 1970, not because they were pessimists, but because they were being rigorous. Their singularity theorems showed that under the very conditions general relativity itself describes, the universe must have had a beginning, a point of infinite density that the theory can predict but never explain. Infinite density is not a bigger version of anything felt on Earth. Not the crush of the deepest ocean trench. Not the weight of a mountain overhead. It is the mathematics simply giving up, the way a calculator returns an error instead of a number when asked to divide by 0. General relativity hands you a door made out of its own equations and then refuses to describe what's on the other side of it. There was no before the beginning, only the beginning arriving. But the wall itself was never the real mystery. The real mystery is what happens the moment someone asks what's behind that door. Because in 1982, a Ukrainian-American physicist worked out a version of an answer that other physicists found difficult to sit with. Not because his mathematics was wrong, because of what it implied nothing had been doing all along. Alexander Vilenkin's equation starts from a question that sounds almost too simple to matter. What if the universe didn't come from something shrinking down to nothing, but from nothing expanding up into something? To understand why a serious physicist would ask that, it helps to first let go of what nothing usually means. An empty room, a blank page, silence with nobody in it. In quantum mechanics, there is no such thing as true silence. Werner Heisenberg's uncertainty principle says that energy and time can never both be perfectly zero at the same instant, which means that even a patch of space with nothing in it, no atoms, no light, no matter of any kind, is still allowed to borrow a tiny amount of energy for an impossibly short moment and give it back before anyone could object. Physicists call the result virtual particles, pairs that flicker into existence and vanish again faster than anything could ever measure them directly. Not a philosophical claim, a measured one. In 1948, the Dutch physicist Hendrik Casimir predicted that if you placed two metal plates close enough together inside a total vacuum, the empty space between them would produce a real, physical force pressing the plates together with the very nothing that was supposed to be pressing on nothing at all. The prediction would sit essentially unconfirmed for almost 50 years, until a 1997 laboratory measurement finally caught the vacuum in the act, at a strength within a few % of what the equations had always said it should be. The force is tiny, far too small to notice between anything wider apart than a human hair, but it is there, and it is real, which is the entire point. Here's the part that changes how you might picture your own two hands. Right now, wherever you're resting, the space between them is doing this. Not occasionally, but constantly, without asking permission. No one has ever touched, or breathed, or fallen asleep inside a true, mathematical nothing. Because as far as physics can detect, that kind of nothing may not exist anywhere in this universe at all. And that is precisely the size of the problem Vilenkin needed to solve. But it is not a problem the vacuum on either side of your hands can answer. Quantum vacuum fluctuations are real, tested, and useful. But they still need space to fluctuate inside and time for the fluctuation to unfold across. Vilenkin was not trying to explain how something appears inside space. He was trying to explain how space itself, and time along with it, could appear from a state that had neither one. That is not the same question with smaller numbers. It is a harder question wearing the same clothes. The difference between explaining why a wave rises and explaining why the ocean exists to hold it at all. In 1982, Vilenkin published an equation that claimed to answer the second question anyway. Vilenkin's equation belongs to a strange corner of quantum mechanics called tunneling. The same mathematics that lets a particle appear on the far side of a barrier it never had enough energy to cross, as if it borrowed the barrier's permission for an instant and paid it back before anyone could check the books. Tunneling isn't some laboratory curiosity. It's the reason the sun burns at all. Without it, the protons crushed together at its core would be too far apart, moving too gently, to ever fuse into helium and release the light now reaching you. 8 minutes late on whatever surface you're resting on tonight. Hold that for a moment. That same law of borrowed permission is what Vilenkin reached for to ask how an entire universe could begin. His version starts from what physicists mean by nothing in the strictest sense the mathematics allows. No space, no time, no energy, not even the quantum vacuum from a moment ago, because a vacuum still needs space to be a vacuum of. Just a geometry of zero size, described by an equation with one deeply unsettling property. It does not forbid a transition to a small, curved, expanding universe. It assigns that transition a probability, not zero. Small, but never zero. Not a creation event in the way the word usually gets used at all. Not an explosion, not a decision, not a cause reaching backward to produce an effect somewhere ahead of it. A tunneling a universe appearing the way a proton fuses, the way a particle slips through a wall it has no business crossing, following a probability that was, in some sense, sitting inside the mathematics the entire time, waiting for nothing to ask. But here is the question that keeps physicists awake at conferences instead of resolving anything for them. A probability has to be a probability of something, governed by rules that exist somewhere for it to obey. If there was truly nothing before the tunneling, no space, no time, not even a vacuum humming to itself, what were the rules even written on? Vilenkin's own answer is unsettling mostly because of how honest it is. The laws of quantum mechanics themselves may not require space or time to exist in the first place. They may be more fundamental than the universe they go on to describe, floating free of anywhere to be written down. Whether that answer satisfies the question or simply moves it one step further into the dark is something even Vilenkin has never claimed to have settled. It might be worth letting that unresolved feeling sit with you for a moment, because it will return, in different clothing, in almost every idea you hear about tonight. No one working on the proposal in 1982 could have known that inflation, the very theory built to explain what the tunneling seed grew into, would eventually hand Vilenkin a new role, co-author of a theorem that would come back to haunt inflation itself. But tunneling only explains how a seed the size of nothing could appear. It does not explain why that seed, once it existed, grew into 100 billion galaxies instead of collapsing straight back into whatever nothing it came from. Answering that requires an idea even stranger than the tunneling itself, an inflation that, once it starts, may never actually be able to stop. Now hold that seed for one more moment. Add to it something Alan Guth worked out in 1979, publishing it 2 years later, a mechanism that could take a region of space smaller than a single proton and double its size roughly once every 10-trillionth of a trillionth of a trillionth of a second, for around 100 doublings in total, before slowing back down to the gentler expansion astronomers measure today. That mechanism is called inflation, and it was never invented to explain the beginning. It was invented to fix two smaller, more technical problems. Why the cosmic microwave background reads the same temperature in every direction, even across regions of sky that, under ordinary expansion, could never once have touched each other, and why the geometry of space is flat rather than curved, to a precision better than 1 part in 100,000. Flat, here, doesn't mean shaped like a pancake. It means that if two beams of light traveled in perfectly parallel lines across the universe, they would still be perfectly parallel to each other billions of years later. Instead of slowly converging or spreading apart, the way they would on the curved surface of a sphere or a saddle, getting a universe that flat by accident, without inflation, would be like balancing a pencil on its tip and having it stay there for 13 billion years. Guth needed an engine that could stretch a single connected patch of space large enough to cover the entire sky visible tonight. Inflation was that engine. If you shrank the doubling down to something a body could feel, it would be closer to a single heartbeat, swelling to the size of the solar system before the next heartbeat even started. But it's what happened next that turned a technical fix into something closer to a creation story. In 1983, the physicist Andrei Linde noticed something uncomfortable about the field driving inflation. Because it obeys quantum mechanics, it doesn't decay evenly everywhere at once. In some patches, it collapses into ordinary space and matter, becoming, eventually, a universe like this one. In most patches, quantum randomness keeps the field inflating instead, faster than the patches that already stopped could ever catch up to it. The reversal buried inside that sentence is easy to miss the first time you hear it. Inflation does not end everywhere at once. It ends in scattered pockets, bubbles, while the space around and between those bubbles keeps expanding forever, faster than anything inside them could ever travel to reach the next one over. Linde called it eternal inflation, and the name isn't poetic exaggeration. In his equations, once inflation starts, it does not stop. It cannot stop. Somewhere, always, more of it is happening than has ever finished. This universe, every galaxy, every star, this exact night would be only one bubble, cooling and slowing down inside a field that, everywhere else, is still doubling. Inflation would go on to become the leading framework in cosmology for the next 4 decades, backed by measurements no one, in 1979, had the instruments to make. And it would also, without anyone intending it, make the exact problem it was built to avoid reappear in a stranger, larger shape. In 1992, a NASA satellite named COBE sent back a map that made grown scientists weep in a press conference. Not because the universe looked beautiful, though it did, but because it looked correct. COBE had been built to search the cosmic microwave background, the faint microwave glow left over from 380,000 years after the beginning, for tiny variations in temperature, patches barely 1 part in 100,000 warmer or colder than their neighbors, that this exact frozen pattern would spend the next 3 decades being checked, rechecked, and never once found wrong. Inflation had predicted those variations should exist before anyone had the instruments to look for them. The theory said the same quantum fluctuations responsible for Vilenkin's tunneling and Casimir's flickering vacuum should have been stretched by inflation's expansion from sizes smaller than an atom to sizes larger than galaxies, freezing tiny random noise into the seeds every future galaxy would eventually grow from. George Smoot, the astrophysicist who led the COBE team, described the map in words that made the front page of newspapers that had never run a cosmology story before. Structure imprinted on the sky since a fraction of a second after the beginning. Not a metaphor about faith. A literal description of what the data showed. That map is, in a very real sense, the oldest picture you will ever be able to look toward. 13 billion years compressed into a single skin of ancient light. The pattern in that map is not random noise. Either. Baked into it are the fingerprints of sound. Pressure waves that rippled through the hot plasma of the infant universe, the way sound ripples through air, compressing and rarefying matter over and over before light was even able to travel freely. Cosmologists can read the size of those frozen sound waves the way a geologist reads rings in a tree, and from them recover the universe's exact age, its exact composition, and the exact proportions of ordinary matter, and dark energy filling it. Numbers agreed upon by a map that is, itself, 13 billion years old. Every galaxy that will ever hold a star, including the one now warming this room through generations of nuclear fusion, began as one of those fluctuations. 1 pixel too faint for any human eye, frozen into the sky before atoms even existed to see it. 2 later missions, WMAP in the 2000s and Planck in the 2010 seconds, measured the same pattern with far greater precision, and the pattern held to a precision far beyond rough agreement. The exact shape of the fluctuations, their sizes, their statistics, the way they clustered together, matched what inflation had predicted decades earlier, before the technology to test it had even been built. Here's what those numbers don't tell you on their own, though. A matching prediction is not the same as a solved case. Inflation explains why the fluctuations exist. It does not explain why the field that produced them was sitting at exactly the right energy, in exactly the right state, to start inflating in the first place. And that gap is where the next complication begins. In an eternally inflating multiverse, new bubbles are being born constantly, each one a self-contained pocket of ordinary space and time, cooling down from its own moment of inflation ending. Some physicists estimate the process has been running, and will keep running, without any final stopping point at all. Try to hold the number some cosmologists have proposed for how many such bubbles may already exist, and notice how quickly it stops meaning anything. Not millions, not the number of stars in every galaxy combined, but a figure closer to the number of ways you could rearrange every atom in the observable universe. You are not being asked to picture that number. Nobody can. You are only being asked to notice that infinite and a great many stopped being different words somewhere back near the start of this sentence. Not next door, not distant enough that a spacecraft launched today could someday arrive. The space between bubbles isn't slow to cross. It is expanding at every point, faster than light could ever cross it. This isn't a loophole in relativity. Relativity limits how fast anything can move through space. It says nothing about how fast space itself is allowed to grow. An inflating space grows without any speed limit at all. A beam of light leaving one bubble aimed directly at its nearest neighbor would find the distance between them increasing faster than its own approach. For the rest of time, let that arrive slowly. Here's the part that's genuinely difficult to sit with. Not because it's sad, but because it refuses to resolve. If other universes exist in this picture, we are not simply too far away to reach them. We are further away than far is able to describe, in a universe whose own geometry keeps the gap growing on purpose. No telescope built in any future century, no signal broadcast at any strength, could ever close a distance that grows every second faster than the signal crossing it. Physicists who work on eternal inflation have mostly made peace with a strange kind of loneliness this creates, sometimes calling it the multiverse's central irony. A theory built to explain how everything could come from almost nothing accidentally predicts that almost everything it produces will be permanently, structurally unreachable by anything else it produces. It is worth naming plainly. Eternal inflation is not a fringe idea kept alive by a handful of physicists chasing something exotic. Versions of it are treated as the default expectation among cosmologists who study inflation seriously, not because anyone has seen a bubble, but because the same mathematics that already matches the Code map, the WMAP map, and the Planck map keeps predicting more bubbles as an unavoidable side effect, whether anyone wanted the multiverse or not. The multiverse does not solve loneliness. It only makes the loneliness larger. And that, as strange as it sounds, is not even the strangest problem eternal inflation creates. The stranger one is about time itself, because inflation was supposed to be the theory that finally let the universe avoid Hawking and Penrose's singularity. It does not. 3 physicists once sat down to ask a question that sounds almost administrative. Does eternal inflation, mathematically, actually need to have had a beginning? One of the 3 was Alexander Vilenkin, revisiting the tunneling proposal from earlier tonight. Another was Alan Guth, the same physicist who had invented inflation in the first place. The third, Arvin Borda, brought the mathematics that would settle it, publishing the result in 2003 as a theorem that now carries all 3 of their names. Their proof, now called the Borda-Guth-Vilenkin theorem, applies to any universe that has been expanding, on average, throughout its history, which includes every version of eternal inflation ever proposed, with no exceptions carved out for special cases. The theorem shows that such a universe cannot be extended infinitely into the past. Somewhere behind it, at a finite distance back in time, there has to be a boundary, a start. The theorem allows no exceptions. Sit with what that means for a moment. The theory built specifically to describe an eternally self-replicating multiverse. one bubble spawning the next without any need for a first cause, turns out, by the mathematics of its own inventor, to still require one. Not a workaround, later theorists found. Not a beginning pushed comfortably out of reach. Some theorists have proposed narrow loopholes, versions of inflation that might average below the theorem's threshold under specific, finely tuned conditions. None of these attempts has produced a version of eternal inflation that avoids a beginning while still matching everything already observed. The theorem's authors built it precisely to close that kind of escape hatch before it could even be proposed. Guth himself, when asked about the result in public talk since, has said plainly that inflation, whatever else it explains, does not get anyone out of needing a beginning. It is a rare thing in physics for the person who built a theory to also be one of the three people who proved its central promise doesn't fully hold. And rarer still for that same physicist to keep endorsing the theory anyway, simply because every alternative anyone has proposed explains the evidence worse. The wall isn't smaller in this version of events, and it hasn't moved anywhere convenient for science to avoid it. It's the same wall, standing in almost the same place, no matter which of these two theories you're standing inside. This is where Vilenkin's own tunneling proposal and Linde's endless bubbles converge back onto Hawking and Penrose's original singularity theorem from the very start of tonight. Three completely different approaches, built by people who mostly weren't trying to agree with each other, all arriving at the same closed door. But here's what almost nobody considers when they hear this. A door that three unrelated proofs all arrive at isn't necessarily a wall. Sometimes it's a sign that everyone has been asking the door the wrong question. And in 1983, the same year, Linde proposed eternal inflation. A very different physicist proposed that the question itself, what happened before the beginning, might not be a question physics is even able to ask. It's a question you're about to watch fall apart in one of the most elegant ways physics has ever managed. In 1983, James Hartle and Stephen Hawking published a paper with a modest title, Wave Function of the Universe. That tried something almost nobody before them had attempted. Instead of asking what caused the beginning, they asked whether what caused the beginning was even the right shape of question to ask about time itself. Their tool was a piece of mathematics called imaginary time, and the name is more literal than it sounds. In their equations, very close to the beginning, ordinary time is treated as if it behaved like an extra direction of space rather than like time at all. That substitution does something strange to the singularity that had stopped Hawking's own earlier theorems cold. It smooths out. The sharp point where the equations used to explode into infinity becomes, instead, an ordinary, rounded patch of geometry, with nothing marking it as special. Now hold a globe in your mind and find the North Pole. Stand on it and ask which direction is north. There isn't one. North is a direction you travel across the Earth's surface, and the North Pole is simply the point where that direction runs out of room to mean anything. Not a hole, not an edge, not a wall anyone could fall through. The surface itself stays completely smooth there. It has no boundary at all, while still being entirely finite. Nobody could ever sail off the edge of the Earth, and nobody would ever need infinite fuel to explore the whole thing either. This solves something that had quietly embarrassed cosmology for decades. Every other model needs someone, or something, to specify the exact conditions the universe started with, the way a recipe needs a first ingredient measured out before anything can be baked. The no-boundary proposal needs no such measurement. Its initial conditions aren't imposed from outside. They fall out of the geometry itself, the same way a sphere doesn't require a starting latitude to be specified. The shape decides that on its own. This isn't a metaphor bolted onto the equations for the sake of a nice image either. The no boundary in the proposal's name is a precise mathematical condition. The universe, in this picture, has a beginning in time, but no boundary separating that beginning from everything that follows it. The same way a sphere has a topmost point but no edge circling around it. Hold that. Hartle and Hawking's proposal treats the beginning of the universe the same way it treats the North Pole. In their model, Asking what happened before the Big Bang is structured exactly like asking what's north of the North Pole. Not unanswerable, because the answer is hidden somewhere. Unanswerable because the word before stops referring to anything. Once you're standing at that particular point, the idea would go on to earn Hawking his widest public audience yet, folded into the closing pages of a book that sold more than 10 million copies. It would also, 3 decades later, become the center of one of cosmology's most bitter and unresolved arguments. Not about what the proposal means if it's true, but about whether its founding equation produces a sensible number at all. To make the North Pole picture work as actual physics, and not just as a comforting image, Hartle and Hawking needed a specific mathematical move called a Wick rotation, multiplying the time variable in their equations by the imaginary number that mathematicians call I, the square root of -1. That single substitution rotates time, on paper, until it points in a direction indistinguishable from an ordinary dimension of space. Not a trick to dodge the problem, a genuine change in what the mathematics is describing. Under ordinary time, the equations of general relativity treat the past and future as fundamentally different from left and right, forward and back. Time has a direction, an arrow, a one-way quality nothing else in geometry shares. Under imaginary time, that asymmetry disappears. Near the beginning, in this picture, there was no forward yet. There was only shape. This wasn't a new trick invented just to solve the beginning. Hawking had already been using imaginary time for a decade by 1983, ever since his work on the quantum behavior of black holes in the 1970s. The same mathematics that let him calculate, in 1974, that black holes are not perfectly black at all, but leak a faint trickle of radiation and slowly evaporate over unimaginable spans of time. Applying the identical tool to the beginning of everything wasn't a leap into the dark. It was Hawking reaching for the one piece of mathematics he trusted most, and pointing it at the largest question he had left. Think of it less like solving a puzzle, and more like realizing the puzzle was drawn on a Mobius strip. Trace a finger along what looks like 2 separate sides, one labeled before and one labeled after, and discover there was only ever one continuous surface, folded in a way ordinary intuition isn't built to see. None of this required abandoning Einstein's equations either. It required trusting them somewhere stranger than anyone had previously dared to look. Right at the single point where they had always predicted their own breakdown, Hawking put it more plainly than most of his colleagues ever dared to in print. The boundary condition of the universe, he wrote, is that it has no boundary. Ordinary time, with its familiar arrow pointing from past toward future, only switches on once you move away from that smooth beginning. The way north only starts meaning something useful once you've stepped off the exact point of the pole itself. Here's what almost nobody considers about that claim. If time itself only becomes time a short distance away from the beginning, then the question, what happened before time started, isn't being left unanswered by Hartle and Hawking's proposal. It's being quietly retired. Not solved, retired. The way you'd stop asking what's colder than absolute zero once you understood why the question stopped making physical sense at all. Not every physicist has been willing to let the question go that easily. 3 physicists, Jobfeld-Brugger, Jean-Luc Leyners, and Neil Turok once aimed a paper directly at the mathematical heart of the no-boundary proposal. Using a more rigorous technique for handling the kind of complex, imaginary time path, integral Hartle and Hawking's calculation depends on, they argued, in a 2017 paper, that the original computation had taken a shortcut that doesn't actually hold up. Done properly, they claimed, the no-boundary wave function doesn't favor a smooth, gently expanding universe like this one. It favors wild, chaotic geometries. And the universe we live in becomes, on their numbers, almost infinitely unlikely rather than the natural outcome Hartle and Hawking had described. The disagreement lives inside a piece of mathematics called a path integral, a way of calculating the most likely history of a system by, in effect, adding up every possible history it could have taken and letting them interfere with each other, the likely ones reinforcing and the unlikely ones cancelling out. For ordinary physics, that sum is straightforward. For imaginary time applied to the birth of a universe, the sum involves rotating the calculation through the complex plane and exactly how you're allowed to perform that rotation, which mathematical path you take to get there, turns out to change the final answer. Turok's team argued that Hartle and Hawking's original path missed a term that dominates the result once handled correctly. Hertog and Hawking argued the opposite, that Turok's more rigorous method solves a different, less physically meaningful version of the problem than the one cosmology actually needs answered. Hawking did not let the challenge go unanswered. Working with physicist Thomas Hertog through the final months of his life, he co-authored a response defending a refined version of the proposal, arguing that Turok's team had mishandled a subtlety in how the calculation should be framed. That paper, titled "A Smooth Exit from Eternal Inflation," was submitted just before Hawking's death in March of 2018 and published in the weeks after it. One of the last pieces of physics he ever completed, still arguing, to the end, with people trying to prove him wrong. Not because his mathematics was wrong, not because theirs was, either. The dispute, as of tonight, remains unresolved. Both sides have published follow-up papers refining their positions. Neither has produced a version of the calculation the other side accepts without objection. Neither side is accusing the other of dishonesty. Both are world-class mathematicians reading the same equations and arriving at incompatible conclusions about what those equations are actually saying, which is, itself, a quietly unsettling fact about how close to the edge of known mathematics this question sits. This is not a case of physicists being cautious out of habit. It's a genuine, open disagreement about whether one of cosmology's most elegant ideas actually predicts the universe we're sitting inside of, or only appears to if you don't look at the mathematics too closely. Nobody currently working on the problem is willing to predict when it will be settled or whether it ever fully will be. Step back for a moment from Vilenkin's tunneling, from Linde's bubbles, from Hartle and Hawking's smoothed-out pole, and notice what all three approaches share underneath their disagreements. Each one is an attempt to answer a question that assumes causality has to reach backward forever. Something happened, so something before it must have caused it, which means something before that must have caused the cause. On, until you either find a first link or run out of chain to follow. Every one of tonight's proposals eventually meets a version of the same wall Hawking and Penrose found in the 1960s, dressed in different mathematics. Not because the physicists involved lack imagination, because the demand itself. Find the cause of the first cause may not be a demand time is built to satisfy, if time itself is one of the things that had to begin. How do you reckon with a question that keeps producing brilliant, rigorous, mutually incompatible answers instead of a single confirmed one? That question does not have a clean resolution, and tonight will not pretend otherwise. We are going to sit inside it, the same way Hartle and Hawking's universe sits at its own North Pole, without an edge to stand on, and without needing one. That is where tonight is standing right now, inside the sitting, not past it. There was no before the question, only the question, arriving, dressed differently depending on which decade of physics happened to be asking it. Vilenkin dressed it in tunneling probabilities. Linde dressed it in bubbles that can never touch. Hartle and Hawking dressed it in a compass with no north. None of them are wrong so much as incomplete, each one describing a different face of a problem too large for any single mathematics to hold entirely. 3 more attempts are still ahead tonight, and each one will try the same door from a different angle. One insisting the universe never truly began at all, one suggesting it was born inside something far stranger than empty space, and one so vast it makes tonight's bubbles look almost modest by comparison. None of them will close the door completely. That is not a failure of tonight's research. It may simply be what an honest answer to this particular question is required to look like. You did not arrive here from nothing, even if the universe itself may have. Every atom your body is built from was already old before the Earth existed. Forged in stars that lived and died so long ago, their light has never once reached anyone alive to see it. The chain of cause and consequence that produced you runs backward through that stellar wreckage, through the cooling plasma of the universe's own first instant, all the way to whatever tonight's ideas are still circling. And it does not need to reach a first cause to be real. It only needed to happen. Think of the last time a single day felt like it was repeating something. Not identically, but in shape, the way autumn always arrives, wearing a version of the autumn before it. You have never lived inside true repetition. You live inside something closer to a spiral. Familiar shapes, moved slightly forward each time they return. Cosmology has its own version of this instinct. And for a shrinking number of physicists, it isn't just an instinct. It's a mathematical proposal. Every proposal so far tonight has accepted one assumption without much question, that there was a first moment, however strange, however smoothed out, or tunneled into, or endlessly inflating, and that before is the wrong word to use about whatever came before it. But a small, persistent group of physicists has spent the last 2 decades building models that reject that assumption entirely, not by finding a clever way around Hawking and Penrose's wall, by proposing that the wall isn't a wall at all, that what looks like a single, unrepeatable beginning might actually be one turn in a wheel that has been turning for longer than beginning can describe. The oldest version of this idea is almost as old as modern cosmology itself. In the 1930s, physicists, including Richard Tolman, tried building a universe that expanded, collapsed back down under its own gravity, bounced, and expanded again. An endless rhythm instead of a single event. Tolman's model failed for a reason that still haunts every cyclic theory built since. Entropy, the measure of disorder physicists use to track which way time is flowing, does not reset when a universe bounces. It accumulates, cycle after cycle, the way debris keeps collecting at the bottom of the same riverbed no matter how many times the flood recedes and returns. A universe built this way should grow messier, longer-lived, and larger with every bounce, which means tracing the cycles backward should reveal a single first bounce anyway, smaller and shorter than all the ones that followed it. The wheel, run backward far enough, still seems to have a first turn. Tolman published this result in 1934, and it effectively closed the subject for the better part of 70 years. Bouncing universes went from being a promising idea to a textbook cautionary tale, the kind of proposal graduate students learn mostly so they can explain precisely why it doesn't work and why it took decades before anyone dared try again. 2 more recent attempts have tried to solve that exact problem, each reaching for physics Tolman never had access to. One looks nearly 100 years into the future of the universe we can already see, using a mathematics so strange it treats an infinitely large, empty space and an infinitesimally small, dense one as, in a very specific sense, the same shape. The other looks sideways, into extra dimensions predicted by string theory, and proposes that the Big Bang wasn't an explosion at all, but a collision. The mathematician and Nobel laureate Roger Penrose calls his proposal Conformal Cyclic Cosmology, built on a piece of geometry most people never encounter outside a graduate classroom: conformal symmetry. He introduced the idea in 2010, with no way of knowing yet that the very fingerprint he would soon point to as evidence was about to become one of the most contested claims of his career. Stretch a shape, shrink it, and conformal geometry doesn't notice the difference. Only angles and proportions matter to it. Overall size never does. Penrose's proposal starts from an unsettling forecast about the universe's own far future. Trillions of years from now, long after every star has burned out, and even black holes have evaporated away into faint radiation, The universe will contain nothing but massless particles drifting through an almost perfectly empty, endlessly expanding void. Massless particles, photons, gravitons, don't experience distance or duration the way matter does. Without mass, size itself stops being a meaningful concept to them at all. Try, for a moment, to imagine losing your own sense of size the way a photon does. Not shrinking, not growing, but the very question of how big you are simply ceasing to apply to you. The way the question of your favorite color doesn't apply to a number, that is closer to what physics means when it says a photon has no rest mass. Scale isn't hidden from it. Scale was never a property it had to begin with. Here's the reversal that gives the theory its name. A universe with no meaningful sense of scale, Penrose argued, is mathematically indistinguishable from a universe at the very beginning of its own expansion, when everything was compressed into almost no size at all. The unimaginably large, empty future of one universe in this picture becomes, through nothing but a change in mathematical perspective, the unimaginably dense, hot beginning of the next one, not by shrinking back down, by discovering that, at the extremes, infinitely large and infinitesimally small were never actually opposite conditions to begin with. Penrose didn't stop at the mathematics. He went looking for a fingerprint the theory could leave behind. Concentric rings in the cosmic microwave background, faint circular patterns, he argued, could be the imprint of black hole collisions from the universe that existed before this one, bleeding through at the moment of transition. In 2010, he announced he had found them, not because his mathematics was wrong, because other cosmologists, examining the same data with different statistical methods, found the same circular patterns showing up in computer-simulated random noise just as often as they showed up in the real sky. Evidence, they argued, of nothing more than the human eye's talent for finding shapes in static. The rings remain unconfirmed. Penrose has never withdrawn the claim. Penrose is not a fringe figure making a wild claim for attention. He shared the 2020 Nobel Prize in Physics for entirely separate work, proving that black holes are an inevitable consequence of general relativity. Some of the same mathematics behind the singularity theorems discussed earlier tonight. When a scientist of that stature makes an extraordinary claim, the physics community takes it seriously enough to spend years trying to break it. Physicists Paul Steinhardt and Neil Turok, the same Turok who would later challenge Hartle and Hawking's mathematics, proposed a different kind of cycle, built not from Penrose's conformal geometry, but from string theory's extra dimensions. They called it the ekpyrotic universe in 2001, borrowing a Greek word that means conflagration, the kind of fire that consumes and renews, rather than simply destroys. Their proposal asks you to picture the universe as one of two enormous, flat, higher dimensional membranes. Brains, in the theory's own shorthand, floating parallel to each other across an extra dimension invisible to anything living inside either one. None of this requires abandoning the 3 dimensions you move through every day. String theory's extra dimensions are usually described as curled up too small to notice, tucked into every point of ordinary space. But the ekpyrotic model asks you to imagine one of them differently. Not curled up, but wide open. A corridor separating our brain from a second one, both of them 3-dimensional worlds as large and detailed as this one. Neither aware of the other except through gravity's pull, the one force in the theory that leaks across the gap. An attractive force draws the 2 brains together, slowly, over unimaginable stretches of time, until they collide. Not gently. On impact, the kinetic energy of the collision converts into an almost unimaginable amount of heat and radiation, filling both brains with matter and energy in what looks, from the inside, exactly like a Big Bang, because from the inside, it is one. Then the brains rebound, drift apart, expand, cool, form galaxies, form stars, form nights like this one, over hundreds of billions of years, before the same attractive force slowly reels them back in for the next collision. The contraction phase leading up to each collision does something inflation's expansion cannot. It takes whatever tiny irregularities existed across each brane and slowly, patiently smooths them toward uniformity, the way a wrinkled sheet pulled taut from every corner at once eventually lies flat. Inflation solves the same uniformity problem by expanding a single small patch until it dominates everything visible. The ekpyrotic model solves it by contraction instead of expansion, which is precisely why it can, in principle, to produce a universe that looks like this one, without ever requiring the runaway inflating field Guth and Linde built their entire proposal around. Now add what this means for the question tonight keeps circling back to. In the ekpyrotic model, there was no single beginning at all, not in the way the Big Bang model or Vilenkin's tunneling describe one. There was a collision, preceded by a long, slow contraction, preceded by the expansion of the cycle before it. In a chain, some versions of the theory extend backward without any first link required, though whether it can actually escape the Borde-Guth-Vilenkin theorem from earlier tonight remains one of the more technical, unresolved arguments in the field. In March of 2014, a team of astronomers working with a telescope called BICEP-2, stationed at the South Pole, called a press conference to announce they had found something extraordinary, a specific pattern of polarized light in the cosmic microwave background called B-mode polarization, that theorists had predicted only primordial gravitational waves from cosmic inflation could produce. If you had been watching a live stream of the March 2014 announcement, you would have seen something rare in a field known for careful hedging. Genuine, unguarded excitement. One cosmologist was filmed being handed the result at his front door and beginning to cry. For a physicist, this was as close as the field gets to footage of the moon landing. The announcement made front pages worldwide. For a few months, it was treated as the closest thing physics had to photographing the moment of inflation directly, and it would have ruled out most versions of the ekpyrotic and cyclic models in a single afternoon, since those theories generally predict a signal too faint to ever be detected this way. Dust in our own galaxy, it turns out, aligns itself along the faint magnetic fields threading through the Milky Way, and in doing so, polarizes the light passing through it in a pattern that can mimic, at certain frequencies, the exact signal gravitational waves were predicted to leave behind. BICEP-2 had observed at a single frequency, unable to tell the two signals apart on its own. Only by combining BICP-2's data with Planck's broader frequency coverage, capable of mapping the dust separately, could anyone finally separate what the sky was actually saying from what everyone had hoped to hear it say. Within the year, independent analysis using dust maps from the Planck satellite showed that the signal BICEP-2 had detected was consistent with polarized light scattered by ordinary dust drifting through our own galaxy, not primordial gravitational waves from the beginning of time at all. By early 2015, a joint analysis between the two teams confirmed it. The signal wasn't nothing. It also wasn't what anyone had spent a year hoping it was. Not a story about scientists being careless. A story about how difficult it is to look 13 billion years into the past without the light from ordinary, nearby things. Dust drifting a few hundred light years away, not 13 billion, getting in the way first. The ekpyrotic and cyclic models, briefly declared dead, are still, as of tonight, very much alive, waiting for an instrument precise enough to tell inflation's gravitational waves apart from a galaxy's ordinary debris. If you take one thing from this particular detour, let it be this. Even the most rigorously reviewed announcement in modern cosmology needed 18 months and a second satellite to know whether it was measuring the birth of the universe or merely the dust drifting between here and the nearest star, cluster. Both of tonight's cyclic proposals share Tolman's old problem in a new coat, and both have spent real effort trying to tailor it to fit. Steinhardt and Turok's answer relies on the sheer scale of the contraction and expansion phases. If each cycle stretches space by an almost incomprehensible factor before the next collision, the disorder accumulated in the previous cycle gets diluted across so much new volume that the next cycle can start looking, for all practical purposes, fresh, even though the total entropy of everything, added up honestly, never actually goes down. Not a loophole in the original problem. A wager that dilution can outrun accumulation. Cycle after cycle, for however many cycles have already happened. Whether that wager holds up over a truly infinite past remains, by most accounts in the field, unproven rather than disproven. A distinction that matters more in physics than it might sound like it should. You have almost certainly felt a smaller version of this same argument somewhere in your own life. The sense that a fresh start doesn't erase what came before it so much as carry it forward in diluted, harder to see form. Physicists arguing about entropy dilution across cosmic bounces are, in a strange way, debating the same question at a scale that makes the comparison almost embarrassing to make out loud. Does anything ever actually begin clean, or does it only ever begin diluted enough to feel that way? And that, quietly, is the same wall again, wearing its fourth costume of the night. Tolman's bounce needed a first bounce. Penrose's eons, run backward far enough, still ask what came before the first one. Steinhardt and Turok's brains still owe an answer for how long they've been colliding, and whether how long is even a question with a final number attached to it. 4 different teams of physicists, working across 7 decades, 4 completely different mathematical toolkits: general relativity, quantum tunneling, conformal geometry, string theory, and 4 times the wall reappears in a new shape. Never quite gone, never quite unavoidable either. Notice too what hasn't happened across any of tonight's 4 attempts so far. Not one of them has been laughed out of the field. Not one has been quietly abandoned by the physicists who built it. They remain open, debated, funded, published. Which tells you something the wall itself has been telling you since the very first minutes of tonight. This isn't a case of bad ideas failing to hold up. It's a case of a question hard enough that even wrong turns keep looking, for years at a time, like they might be right ones. There is a 5th proposal left for tonight, and it starts from a place stranger than any bubble, any bounce, or any collision. Not in empty space at all. Inside, the one object in this universe already known to bend the rules of space and time past the point of ordinary description. In 2010, a physicist working at Indiana University published a paper with a title almost nobody outside the field would think to click on: Cosmology with Torsion, an alternative to cosmic inflation. Buried inside, it was one of the strangest serious proposals in modern physics, not yet tested against a strange, unexplained pattern already sitting in the oldest light in the sky, a comparison other physicists wouldn't draw for years. Nikodem Popławski's idea starts from a detail most introductions to general relativity leave out entirely. Einstein's original theory describes gravity using the curvature of space-time alone, but a lesser-known extension called Einstein-Cartan theory adds a second ingredient, called torsion, tied to the intrinsic spin of every particle of matter. Under ordinary curvature, a collapsing star has nothing to stop it from crushing down to an infinitely dense point. The same singularity Hawking and Penrose proved was unavoidable at the start of tonight. Under torsion, something new happens. As matter collapses toward that point, the spin of every particle inside it generates an intense repulsive force, one too faint to matter under any ordinary conditions, but strong enough, at extreme densities, to halt the collapse entirely and throw it back outward. Not an explosion visible from outside. From outside, the black hole looks like every other black hole, dark, spinning, swallowing anything that crosses its horizon. But on the other side of that horizon, in Popławski's mathematics, the halted collapse doesn't simply stop, it rebounds, and the rebound opens into an entirely new region of expanding space-time. Disconnected from the universe the original star collapsed inside of. Sealed off, self-contained, its own Big Bang, wearing a black hole's event horizon as its only visible trace from the outside. Torsion is easiest to picture as a kind of twist layered on top of ordinary gravity's curve. Curvature is what makes a trampoline sag when you stand on it. Torsion would be what happens if the trampoline's fabric were also made of countless tiny arrows. Each one, a particle's spin, all twisting the surface in a direction curvature alone could never produce. At everyday densities, that twisting is so faint it has never been measured by any instrument built. Compress matter far enough, though, past the density of an atomic nucleus, and Popławski's equations say the twisting becomes the dominant force in the room, powerful enough to overwhelm gravity's own pull and shove the collapse back outward, instead of letting it continue to a singularity. Nothing about you, resting in the dark right now, needs to worry about this force. The densities involved are roughly 14 orders of magnitude beyond anything a human body, a planet, or even an ordinary star will ever approach. This is physics reserved entirely for the last, violent moments of a massive star's collapse. That gap in scale is worth holding on to for the rest of tonight's final proposal, not a metaphor for how dramatic a black hole feels to fall into. A specific, published mechanism, using an established extension of general relativity for how a genuinely new universe could begin inside one. Here's what makes Popławski's proposal harder to dismiss than it sounds on first hearing it. It isn't only a story about the past, it's a claim about right now. About every black hole currently sitting at the center of every galaxy overhead, actively pinching off children of its own on the other side of an event horizon. Nobody outside it will ever be able to see. If the mechanism is real, our own universe could be exactly this kind of child, born inside a black hole that formed somewhere in a larger, older parent universe, one whose own sky, own stars, own physics we would have no way of ever detecting. And because Popławski's model inherits the rotation of the collapsing star that formed the black hole, it makes an unusually concrete, almost reckless prediction. A universe born this way should carry a faint, leftover preferred axis, a whisper of the direction its parent black hole was spinning. Cosmologists already have a name for a strange, still unexplained anomaly in the cosmic microwave background, the axis of evil. An unexpected alignment between the largest scale patterns in the CMB and the geometry of our own solar system, first noticed in WMAP data in the early 2000s and still present, weaker but not gone, in Planck's later measurements. Most cosmologists suspect it's a statistical fluke or an artifact of how foreground light gets subtracted from the data. Popławski has pointed to it as exactly the kind of leftover signature his model would predict. Picture, for a moment, standing at the center of that inherited spin, the way you might stand at the center of a slowly turning room and only notice the rotation by watching how the walls drift past, rather than by feeling anything pulling at your own body. That is roughly the scale mismatch involved. A rotation imprinted across the entire visible universe, from a single collapsing star's spin, stretched by billions of years of expansion into something so gentle it would show up only as the faintest possible statistical whisper in the oldest light there is. The Event Horizon Telescope captured the first image of our own galaxy's central black hole, Sagittarius A, in 2022. 4 million times the mass of the Sun, sitting 26,000 light-years from here, a ring of light bent around a darkness no signal has ever escaped. If Popławski is right, something is happening on the far side of that darkness right now, at this exact moment, that no equation from any of tonight's other 4 proposals even attempts to describe. You will likely never look at a black hole the same way again after tonight, whether or not Popławski turns out to be right. That alone might be worth more than the proof anyone is still waiting on. Not proof, a coincidence energetic enough that it hasn't been fully explained away yet, sitting in data every major survey has independently confirmed is actually there. It would be dishonest to leave tonight's fifth proposal sounding more accepted than it is. Torsion itself is not fringe physics. Einstein-Cartan gravity is a serious, decades-old extension of general relativity, taught in graduate courses and taken seriously as a mathematically consistent theory. What remains almost entirely unconfirmed is Popławski's specific application of it. The claim that torsion becomes strong enough inside a collapsing star to halt the singularity and produce a new universe on the other side. No experiment has ever measured torsion directly. The densities where it should matter, according to the theory, only exist inside neutron stars and the final moments of gravitational collapse, places no instrument built has ever been able to probe. The overwhelming majority of cosmologists studying the beginning of the universe still consider inflation, tunneling, or the no-boundary proposal far more likely to be correct, precisely because those ideas connect to more of the evidence already gathered tonight, from the CMB's fluctuations to the flatness of space itself. It's worth being honest with yourself about why a proposal like this one is so easy to find compelling regardless of the evidence. It answers the question tonight keeps circling with an image, not just an equation, and the human mind reaches for images long before it reaches for statistics. That pull toward the vivid explanation over the well-supported one isn't a flaw unique to you. It is, if anything, the exact instinct. Working scientists spend their careers training themselves to resist, not because Popławski's mathematics contains an error anyone has found, because an idea can be internally consistent, mathematically rigorous, and still be sitting on almost no observational ground to stand on. Consistency was never the same thing as proof. The proposal does have one unexpected cousin. In 1992, the physicist Lee Smolin proposed something similar from a completely different angle, calling it cosmological natural selection. If universes really do reproduce through black holes, then universes whose physical constants happen to produce more black holes would leave behind more children, generation after generation, the way biological traits that produce more offspring spread through a population. Given enough cycles, Smolin argued, the universe we live in should have constants unusually well tuned for making black holes, a claim that remains just as unconfirmed as Popławski's, argued by two physicists who arrived at strikingly similar universes from entirely separate starting points. Smolin's proposal ran into the same wall that limits Popławski's. No one has found a reliable way to test either idea against a universe we could compare ours to. A theory of natural selection needs a population to select from, generation after generation, and cosmology has exactly one universe available for direct observation. Everything else is inference, however careful, built from a sample size of one. You are, in this particular sense, exactly as much evidence as anyone studying this question has ever had access to. One universe, examined as closely as an entire species has managed, still arguing about how it got here, whatever its odds of being correct. Sit with the picture this proposal actually paints, because none of tonight's other four proposals offer anything quite like it. Every black hole, in this account, isn't an ending. It's a birth in progress, a sealed door with an entire universe unfolding somewhere behind it, at a pace and on a timescale nobody on this side will ever be able to witness. The supermassive black hole at the center of this galaxy, 4 million times heavier than the Sun, could be one such door. So could every stellar mass black hole scattered through the Milky Way's disk, leftover corpses of stars that finished burning long before the Earth existed. There are, by conservative estimates, on the order of 100 million stellar mass black holes scattered through this galaxy alone, most of them dark, uncatalogued, drifting between the stars you can actually see. Multiply that by the roughly 2 trillion galaxies within reach of current telescopes, and the number of potential nurseries, if Popławski's mechanism is real, stops being countable in any way, a human mind can hold on to for more than a few seconds at a time. Every one of those black holes is also, in an important sense, already ancient. The first stars massive enough to collapse into black holes are thought to have formed within a few 100 million years of the beginning tonight keeps returning to, meaning some fraction of tonight's potential nurseries have already been quietly running for well over 13 billion years. Longer than this universe has had galaxies, longer than it's had anything resembling the sky you'd recognize. If Popławski is right, the sky isn't only full of history. It's full of first chapters, still being written, each one utterly inaccessible to the universe that produced it. 4 theories in, the same pattern keeps repeating itself in new disguises. Tunneling from nothing, bubbles that can't touch, a pole with no north, a wheel with no first turn, and now a birth sealed behind an event horizon. Every proposal solves the wall in its own vocabulary. Not one of them lets anyone actually walk around to the other side and look. Sit with that inaccessibility for a moment, because it's different in kind from the loneliness eternal inflation produced earlier tonight. Linde's bubbles are unreachable because the space between them expands too fast to cross. Popławski's child universes are unreachable because they exist structurally on the far side of a boundary that erases the very concept of far side. The instant anything crosses it, you could point a telescope at every black hole in the sky for the rest of your life and never receive so much as a single photon, confirming or denying whether a universe is unfolding inside any of them. There is one proposal left for tonight, and it doesn't try to explain away the wall at all. It multiplies it into more versions of itself than any of the other 4 ever dared to count. String theory begins from an idea most people have heard of, even without knowing where it came from, that the smallest building blocks of reality aren't points, but impossibly tiny vibrating strings, and the particular note each string vibrates at determines which particle it appears to be. To make the mathematics work without contradicting itself, string theory requires the universe to have 10 dimensions, not 4. 6 more than the length, width, height, and time you move through every day. According to the theory, they're curled up impossibly small, folded into intricate shapes called Calabi-Yau manifolds at every single point of ordinary space, too tightly wound for any instrument to ever unfold and see directly. None of this curling happens somewhere separate from you. If string theory is correct, 6 extra dimensions are folded into the empty space around you right now. At every single point, at a scale roughly 10 million billion times smaller than the smallest thing any particle collider has ever probed directly. String theory didn't set out to produce a landscape this large. It set out to do something no other framework has managed. Describe gravity and quantum mechanics inside the same mathematics without either one breaking down. That unification is still the reason a significant fraction of the world's theoretical physicists have spent entire careers on it. Landscape, problem, and all. The payoff, if it's correct, would be the single deepest theory physics has ever produced. Nobody chose the landscape on purpose. It arrived as an unintended consequence of taking the theory's own mathematics seriously. And here is the detail that turns an already strange theory into tonight's final proposal. The exact way those 6 dimensions get folded determines the physical constants of whatever universe unfolds around them. The mass of an electron, the strength of gravity, whether atoms can even hold together at all. In 2000, physicists Raphael Bousso and Joseph Polchinski calculated roughly how many distinct ways those extra dimensions could be folded and still produce a mathematically consistent universe. The number they arrived at, refined by later work from Leonard Susskind and others, is difficult to say out loud without it sounding like an exaggeration. Something on the order of 10 multiplied by itself 500 times. A number nobody in that first calculation expected would become the central target of an entire rival research program a decade later. Built specifically to prove most of it wrong, not 500 universes. 10 followed by 500 zeros of them, each one a different possible folding, each one a candidate recipe for an entire cosmos with its own laws. Susskind gave this vast catalogue of possibilities a name that stuck: the string landscape. And here's where tonight's second proposal walks back in through the side door. If eternal inflation is correct, every one of those 10 to the 500 foldings isn't just a mathematical possibility sitting on a shelf. It's a candidate false vacuum, and Linde's mechanism from earlier tonight would nucleate bubbles out of every single one of them. Forever, each bubble inheriting whichever folding happened to be sitting nearby when it formed. If most of the 10 to the 500 possible universes are real, only sitting elsewhere, an old and uncomfortable question gets a new kind of answer. Why do the constants of this universe happen to fall in the narrow, specific range that allows atoms to form, stars to burn steadily for billions of years, and chemistry complex enough to build something that can ask the question in the first place? Not because this universe is special, because every bubble with the wrong constants, gravity too strong or too weak, or the strong nuclear force tuned even slightly differently than it is, either collapses back on itself in an instant or expands forever too thin and cold for a single atom, heavier than hydrogen, to ever form. No one is present in those bubbles to notice the absence. You could only ever find yourself doing exactly what you're doing right now, inside one of the vanishingly rare foldings where the numbers happen to land in a survivable range. This reasoning has a real, working name in physics: the anthropic principle, and it produced one of the most striking predictions in the history of cosmology. In 1987, the physicist Steven Weinberg used exactly this logic to predict that the cosmological constant, the mysterious value behind what would later be called dark energy, had to fall within a narrow range, or galaxies could never have formed for anyone to exist and measure it. 11 years later, in 1998, two independent teams of astronomers measured the actual value for the first time. It landed inside the range Weinberg had predicted, using nothing but the requirement that someone had to be around to measure it. Sit with how unusual that is in the history of physics. Predictions normally come from a mechanism. A theory describes how something works, and the number falls out of the description. Weinberg's prediction came from something closer to a filter, not a mechanism explaining why the constant has that value. Only a requirement that whatever the value turned out to be, it had to be compatible with the existence of someone able to ask the question. That is a genuinely strange kind of successful prediction, and physicists are still debating, decades later, how much weight it should be allowed to carry. None of this implies anything was designed or intended. The anthropic principle isn't an argument for purpose behind the numbers. It's closer to noticing that you'll never find a fish complaining about how perfectly the ocean happens to be filled with water. Not because the ocean was built for the fish, but because a fish that couldn't survive outside water was never going to be the one doing the complaining. Not proof that the landscape is real. A working prediction made in advance from reasoning that only makes sense if something like the landscape, or at least a great many failed universes never observed by anyone, is sitting behind this one. Here's the reversal that keeps the string landscape from being treated as a triumphant answer rather than a controversial one. A theory that predicts every possible universe is, by the ordinary standards physicists hold every other theory to, in danger of predicting nothing at all. Science generally requires a theory to rule something out, to say clearly what an experiment should and shouldn't find, so a wrong idea can be caught being wrong. If the landscape genuinely contains close to every mathematically consistent set of physical constants, then almost any measurement anyone could ever make is compatible with some universe somewhere in it. In 2014, the physicists George Ellis and Joe Silk published an essay in the journal Nature with a title blunt enough to make headlines on its own: Defend the Integrity of Physics. Their argument was that ideas this difficult to test were quietly being treated as confirmed simply because they were mathematically elegant, and that physics needed to hold the line against explanations no experiment could ever, even in principle, rule out. Their essay didn't argue the string landscape was false. It argued something more unsettling for working physicists to hear: that a theory attractive enough, mathematically, can start being treated as true well before anyone has found a way to test it, and that the field needed a clearer line between physics and what Ellis and Silk called, pointedly, faith-based physics. The phrase landed hard enough that theorists on the other side of the debate are still quoting it back a decade later, usually while disagreeing with it. It's worth admitting plainly: nobody writing or narrating tonight's program knows which side of this argument is right, and neither does anyone currently working inside the field. You are not missing a piece of settled knowledge that experts already have and simply haven't gotten around to telling you. The uncertainty is the actual, current state of the science, not a simplification made for a program meant to help you sleep. Not every string theorist has accepted the landscape as the final word, either. The physicist Qumran Vafa has spent the last decade building what's now called the Swampland program, arguing that most of the 10 to the 500 foldings Buso and Polchinski counted aren't actually consistent with quantum gravity once you look closely enough. That the true number of workable universes may be a tiny, restrictive sliver of the landscape, not the sprawling catalogue Susskind described. Vafa's Swampland conjectures try to draw a hard boundary between two categories: the landscape, consistent theories that could actually describe a real universe, and the far larger swampland surrounding it. Mathematics that looks like valid physics right up until it's checked against quantum gravity's deeper requirements and falls apart. If Vafa is right, most of what Susskind counted was never real estate at all. It only looked like it from a distance. Elegant mathematics has never once been required to describe a real universe. The argument tonight remains unsettled between physicists working from the same equations. 7 proposals, spanning 80 years since Tolman's first bounce, built from tunneling probabilities, inflating bubbles, a pole with no north, a far future indistinguishable from a beginning, 2 sheets of reality colliding, a birth behind an event horizon, and a landscape of 10 to the 500 possible foldings. And not one of them has produced an observation the entire field of physics agrees settles the question of how this began. That is not, by itself, a failure. Notice what each attempt actually accomplished along the way, even without delivering a final answer. Vilenkin's tunneling showed a beginning doesn't require breaking any law of quantum mechanics. Inflation's bubbles matched a map of the infant universe with a precision no one could have faked in advance. Hartle and Hawking showed the question, what came before time, might not be a coherent question to begin with. Penrose showed that an ending, mathematically, can double as a beginning once the thing being measured changes. Steinhardt and Turok showed a beginning doesn't have to mean a beginning of everything, only of this particular chapter. Popławski's black holes showed the ordinary objects filling tonight's sky might already be doing this, right now, without any fanfare. And the landscape showed that even the fantastically specific numbers this universe runs on might not need a designer, only enough failed attempts sitting somewhere unseen. 7 unfinished sentences, all reaching toward the same word, and not one of them has been allowed to finish it yet. You do not need to choose a favorite among tonight's 7 before you're allowed to sleep. Physicists who have spent entire careers on a single one of these proposals still haven't chosen, and they're awake, arguing about it, at conferences happening on the other side of the planet from wherever you're lying right now. What tonight actually offered wasn't an answer. It was a tour of exactly how far, seriously, rigorously, mathematically, human beings have been willing to chase a question this old. None of tonight's 7 physicists knew, when they first published, that their separate proposals would one day be read back to back in a single sitting by someone falling asleep to all 7 at once. That chase started, in its modern form, with a mathematician working alone in London in 1965, and it has not stopped moving since, carried forward by researchers on at least 4 continents across 6 decades, none of them working for a single institution, a single country, or a single funding source. No one owns this question. It has simply been passed forward, era after era, by whoever happened to be standing close enough to take the next swing at it. None of that effort has produced the one thing tonight opened by promising a settled answer to why there is anything instead of nothing at all. What it has produced, across 60 years and 4 continents and mathematics most people will never read in the original, is something quieter and in its own way sturdier than an answer. Proof that the question itself has never once been treated as unaskable, even by the people best equipped to know how hard it actually is. The physicist Lawrence Krauss once published a book with a title that promised more than any of tonight's 7 proposals ever quite claimed for themselves: A Universe from Nothing. It appeared in 2012. Its argument leaned heavily on ideas from earlier tonight: quantum fluctuations, tunneling, the strange behavior of the vacuum, assembled into a case that physics had finally explained why there is something instead of nothing at all. Not everyone agreed the case held together. Later that year, the philosopher David Albert reviewed the book for the New York Times, and the review became almost as widely read as the book itself. Albert's objection was precise. Everything Krauss called nothing, the quantum vacuum, the relativistic fields, the laws governing how tunneling and fluctuation behave, was still, in the most basic sense, something. It had structure. It obeyed equations. It had the capacity to produce a universe, which is not a capacity philosophical nothingness, the complete absence of laws, mathematics, and possibility itself, has ever been described as having. Krauss's response to the criticism, delivered across interviews and a later afterword, was that Albert's version of nothing, the philosopher's nothing, with no laws and no mathematics and no possibility whatsoever, might not be a coherent concept at all, might not be a thing that could ever have existed for physics to explain in the first place. Albert's response was that this concession, if Krauss meant it seriously, amounted to admitting the book's own title had been a promise physics was never actually going to keep. Neither man backed down in public. The argument, as far as anyone can tell, remains technically unresolved between them to this day. Krauss's nothing and Albert's nothing were never the same word, wearing different clothes. They were 2 different concepts that happened to share a single 4-letter spelling, and most of the confusion in that entire public argument came from nobody agreeing, out loud, which one was actually being discussed. Here's why that argument matters for everything heard tonight, and not just for one book from 2012. Run back through Vilenkin's tunneling, Linde's bubbles, Hartle and Hawking's smoothed pole, Penrose's aeons, Steinhardt and Turok's brains, Popławski's collapsing star, and Susskind's landscape, and notice what every single one of them actually requires in order to function. Not nothing in Albert's sense. Not once. Every proposal tonight needs quantum mechanics to already be true, or geometry to already have rules, or a parent universe to already exist. Something was always already there, waiting to be described. You are not required to resolve the Krauss-Albert argument tonight either, and neither is this program. What's worth carrying from it isn't a verdict. It's the reminder that even the physicists most confident they had finally answered, "Why is there something instead of nothing?" were, within months, forced to specify exactly which nothing they meant. And that specifying it turned out to be most of the actual work, a lesson worth keeping if you ever find yourself certain a hard question has finally been closed. There's a second quieter idea worth carrying alongside tonight's 7, one that doesn't try to answer where the universe came from so much as question whether before ever refers to anything real at all, in any universe, at any point. In 1955, weeks before his own death, Albert Einstein wrote a letter to the family of a friend who had just died, offering the strangest kind of comfort a physicist has ever put on paper, that the distinction between past, present, and future, he wrote, is only a stubbornly persistent illusion. Einstein wasn't speaking loosely. His own equations, taken at face value, describe a universe where every moment, the collapse of the first star, this exact sentence arriving in your ear, and whatever comes after this program ends, already exists, laid out together, with nothing in the physics that marks any one of them as more now than any other. Physicists call this the block universe. Nothing in it moves from potential into actual. It simply is, in full, all at once, the way a single photograph contains an entire afternoon without any part of the photograph having to happen before any other part of it. More recent work pushes the idea further still. In 1983, physicists Don Page and William Wouters proposed a mechanism where time itself might not be a basic ingredient of reality at all, but something that emerges only when one part of a fundamentally timeless universe becomes entangled with another, each one effectively using the other as a kind of clock. Think of two people on opposite sides of a foggy field, each carrying a stopped watch. Neither watch moves on its own, but if the two people start comparing notes, sending signals back and forth, counting how many signals pass between them, something that behaves exactly like time emerges from the comparison, even though neither watch alone was ever actually running. Page and Wouters' proposal treats the entire universe the same way, frozen, overall, and yet producing something indistinguishable from flowing time, wherever two of its parts start comparing notes with each other. Under their proposal, the universe as a whole, described completely, has no time in it whatsoever. Time only appears locally, wherever something inside that whole starts comparing itself to something else. You might notice this in your own experience, right now, listening to this. The way one sentence seems to follow another, the way tonight feels like it's moving towards sleep rather than sitting still. That sensation may be exactly this kind of comparison, happening between different parts of your own brain, rather than proof of some universal clock ticking away beneath you. If either idea is even approximately right, the wall described at the very start of tonight isn't hiding a before that physics simply hasn't found the tools to see yet. There may never have been anything to find. Not because the answer is difficult, because the question quietly assumed time was the kind of thing that could have a before, and that assumption may not survive contact with the deepest physics anyone has ever written down. Every proposal heard tonight arrived by a different route, built from different mathematics, defended and attacked by different physicists across different decades. And yet, laid side by side, they share a structure almost none of them were designed to share on purpose. Not one describes an event happening inside an existing flow of time. Every one of them describes time itself, or space itself, or causality itself, switching on. That distinction is easy to hear and still miss the size of. Ordinary events need a before. A match needs an unstruck moment before it's struck. A birth needs a pregnancy before it. A sunrise needs a night before it arrives. Tonight's questions smuggled that same requirement onto the biggest event there is, assuming the beginning of the universe needed a before in exactly the way a sunrise does. An existing stretch of time for the beginning to arrive inside of, with causality already running, waiting for something to happen. Not one of tonight's 7 proposals accepts that assumption once you look closely enough at what it's actually claiming. Vilenkin's tunneling doesn't happen in time. It produces time as part of what tunnels into existence. Hartle and Hawking's smooth pole doesn't have an edge in time for a before to stand on. Ordinary time only switches on once you've moved away from it. Popławski's collapsing star doesn't create a new universe inside the old one's clock. It seals off an entirely separate clock, running on its own. Even the block universe and the Page-Wouter's proposal from a moment ago describe time as something that emerges from relationships between things, not a container those things were dropped into. Linde's endlessly inflating field doesn't wait inside a pre-existing timeline for the right moment to start. Wherever it is, by definition, it has already always been running. Penrose's aeons and Steinhardt and Turok's colliding brains don't reach backward to a first tick of a clock either. They reach backward to a geometry that simply repeats, indifferent to whether anyone calls a given repetition the first one. Not once, across any of them. Here is the reorganization worth carrying to sleep tonight. The one thing every proposal agreed on, despite agreeing on almost nothing else, the demand for a cause of the first cause, a before of the very first before, may not be a demand reality was ever obligated to satisfy. Not because the answer is hidden somewhere physics hasn't looked yet, because the question, at its deepest point, may be structured the same way what's north of the North Pole is structured, grammatically perfect and empty of anything for physics to find. This does not make the 7 proposals interchangeable, or the search for which one is correct pointless. It changes what finding the right one would actually mean, not the discovery of what came before the universe, the discovery of exactly how and exactly why before ran out of road. Earlier tonight, this program promised not to pretend the central question had a clean answer. And it hasn't broken that promise once, across 7 proposals and 2,000 years of the same argument wearing new equations. That was never a failure of research. It was the honest shape of a question that asks reality to explain its own permission to exist. You have spent tonight sitting inside exactly the tension that was promised at the start. Something happened, and the ordinary human instinct, the one that has never once been wrong about anything smaller than this, insists something must have caused it, and yet every rigorous attempt to trace that chain of causes back to its source arrives, again and again, at a point where cause itself stops being a word with anywhere left to point. Notice what your own body has been doing with that tension for the length of this program. Not resolving it, not needing to, holding it, the way you hold a note in music that never quite finds its way back to the home chord, and somehow doesn't need to for the piece to feel complete. 7 physicists' worth of careers, in 7 different countries, across 7 decades, have been spent learning to hold that same unresolved note without flinching from it, and calling the holding itself a kind of progress. This is not resignation dressed up as wisdom. Physicists chasing tonight's 7 proposals are not people who gave up on finding an answer and decided to feel good about failing. Publishing papers, running the numbers again, waiting for LISA and its successors to return data that might finally rule 2 or 3 of tonight's proposals out for good, holding the tension and continuing to work on it were never opposites. The tension is what keeps the papers coming. You have been doing something structurally similar all night, whether you noticed it or not, staying with 7 unresolved arguments instead of skipping to a verdict, letting the tension build across theory after theory without demanding early relief from any of them. That is not a small thing to have done. Even lying down, even this close to sleep, unresolved chords appear constantly in music precisely because human ears find them more interesting to sit inside than resolved ones. Not despite the tension, but because of it. A resolved chord ends the listening, and an unresolved one keeps it going. Whatever is happening in a body that finds a question like tonight's compelling rather than merely frustrating, may be running on a similar principle. The not knowing, doing quiet, generative work that a tidy answer would have shut down the moment it arrived. There was no before the beginning. There was no before the question. Both of those were true the moment they were said tonight, and both remain true now. Unresolved patient, exactly where they were left. Zoom all the way back out, past the landscape's 10 to the 500 foldings, past Popławski's sealed-off nurseries, past Steinhardt and Turok's colliding sheets, past Penrose's far future disguised as a beginning, past Hartle and Hawking's pole, past Linde's unreachable bubbles, past Vilenkin's tunneling equation, all the way down to the one place every single proposal tonight was ultimately trying to explain: this exact room, this exact breath, this exact stretch of time passing while you listen. The light finally reaching your eyes tonight, if any is still on, left its source years or centuries or millennia ago. The calcium holding your bones together was forged inside a star that finished burning long before the sun existed. The universe you are lying inside of is 93 billion light-years across at minimum. And every part of that distance, every galaxy inside it, every possible pocket universe tonight discussed touching or never touching this one, is still, in some sense, the same conversation the Planck wall from the very beginning of tonight was already having, 13.8 billion years ago, before there was anyone anywhere to listen to it. That distance is worth sitting with on its own terms for a moment, apart from anything else discussed tonight. 93 billion light-years is not how far light has travelled since the beginning. It is how far apart 2 points in space have drifted, while their light was still crossing the gap between them. Space itself stretching underneath the journey the entire time. Nothing physical moved faster than light to create that number. Light leaving a distant galaxy starts its journey as a short, tight wave. By the time it reaches a telescope on Earth, the space it crossed has stretched so much that the wave arrives stretched too, redshifted toward wavelengths no human eye would have recognized when the light first set out. Evidence not of anything racing away, but of the space itself lengthening underneath the journey, the entire time it was underway. The Planck wall from the very start of tonight, and the light only now completing its journey to reach this exact room, are not two separate stories. They are the same expansion, viewed from two different distances, one measured in fractions of a second, the other in spans of time longer than the solar system has existed. The same stretching, the same silent arithmetic, running underneath both without pause. That conversation was never waiting for a guest to arrive after the important parts were finished. Every atom in your body has been part of this exact unresolved argument since roughly 1 second after the beginning, when protons and neutrons first became stable enough to survive being what they are. Tonight's mystery was never something to observe from outside it. You are, and always have been, one of the places it lives. That is not a small claim to make about a single body lying in a single room. It is the same claim every one of tonight's 7 proposals makes about every scrap of matter anywhere, without exception. That nothing sitting inside this universe is a bystander to how it began. Only a still unfolding piece of the argument itself. You have been given, across the last 2 hours or so, 7 different mathematics for one of the only questions that has ever managed to make grown scientists cry at a press conference, sit in bitter disagreement for a decade, or spend an entire career defending a claim almost nobody else in their field currently accepts. It is worth pausing, before tonight closes, to actually say the answer out loud, not the version simplified for a headline, and not the version buried in an hour of technical detail, but the version tonight has actually earned by sitting through all of it. So, how did the universe begin, if nothing existed before it? The most honest answer physics has produced, after 80 years of trying, is not a single sentence. It is 7 stacked on top of each other, each one rigorous enough to survive serious mathematical scrutiny, none of them yet proven beyond the others. It began, perhaps, the way a particle tunnels through a wall it shouldn't have had the energy to cross, borrowing a probability that was, in some sense, always sitting inside the mathematics, waiting. It began, perhaps, inside a bubble of space that is still, right now, inflating forever in every direction except the one this galaxy happens to occupy. It began, perhaps, the way a compass loses its meaning of north at the exact point north is measured from. Smoothly, it began, perhaps, as the mirror image of some almost infinitely distant future, folded back on itself by a geometry that refuses to distinguish the vastly large from the vanishingly small. It began, perhaps, the way two sheets of reality that had been drifting toward each other for longer than how long can describe finally collided, releasing everything they were carrying. It began, perhaps, sealed behind the event horizon of a black hole inside a universe with its own sky, watching one of its own stars collapse into something that would, eventually, become this. Or it began, perhaps, as one folding among 10 to the 500 possible foldings, selected for nothing in particular, except that it was the one folding capable of eventually asking the question out loud. None of the 7 cancels out the others. They are not 7 competitors with one eventual winner and 6 historical footnotes. The way earlier, wrong theories usually get remembered. They may turn out to be 7 descriptions of the same event from 7 mathematically different vantage points. The way a single collision can be described correctly in the language of momentum, or energy, or force, without any one description being more true than the others, only more useful for a particular question. Physics has not yet found the vantage point that lets all 7 collapse into one. It may never find it. That would not make 80 years of careful mathematics a waste. It would make them 7 honest angles on a single event, too large for any one sentence to hold. You were only ever asked to hold 7 of them at once, for one night, not to choose among them before you were allowed to close your eyes. 7 beginnings, 1 wall, still standing behind every single one of them. A beginning. Tonight's 7 proposals agree on this, much if nothing else, is not the same thing as a cause. A cause requires something earlier to have pushed it into motion. A hand reaching backward through time to set the first domino tipping. An arrival requires nothing earlier at all, only the thing itself. Present, real, undeniably here. Whether or not anything ever explains how it got that way. This is not a consolation prize dressed up as a definition, offered because physics couldn't produce anything better. It is what all 7 proposals, examined closely enough, were actually describing the entire time, whether or not the physicists writing them chose to say it out loud. Vilenkin's tunneling universe does not arrive because something caused it. It arrives because the mathematics permitted it, and permission is not causation. It is closer to an absence of prohibition, which is a very different, much quieter kind of event. Linde's bubbles do not arrive because inflation decided the moment was right. They arrive continuously, everywhere the field happens to sit, without any single moment being more of a start than any other. Hartle and Hawking's smoothed universe does not arrive at a point in time at all. It simply is a certain shape, the way a sphere simply is round, without the roundness needing to have been caused by anything external to the sphere itself. Penrose's aeons do not arrive because a previous universe decided to end. Ending and beginning, in his mathematics, are the same geometric event, viewed through 2 different units of measurement, arriving together, inseparably, the way a hilltop cannot exist without the bottom of the next valley existing too. Steinhardt and Turok's brains do not arrive because a collision was scheduled. They arrive because 2 surfaces, drifting for reasons the theory doesn't fully explain, eventually occupy the same place. Popławski's child universe does not arrive because a star decided to collapse into something new. It arrives because torsion, once dense enough, has nowhere left to push except outward, into a new region of space-time that was, in some sense, always the only place left for it to go. And Susskind's landscape does not arrive because one folding was chosen over the others. Every folding arrives, everywhere, constantly. And this one simply happens to be the folding capable of noticing that it did. There was no before you, only you, arriving. And here you are anyway, 13.8 billion years and one impossible wall later, listening to the same argument that produced you still failing to resolve itself. And somehow no less real for that. That is the closest thing to an answer tonight has to offer, and it was never going to arrive wrapped in the comfort a direct cause would have provided. An arrival doesn't explain itself. It doesn't need to. It only needs to have happened the way this exact night happened, the way this listening body happened, the way the universe happened. All three of those arrivals sitting inside the same unresolved, undeniable fact of being here at all. Tonight will not end with the wall falling. No night like this one. No book, no lecture anyone has ever produced has managed that yet. What tonight can end with, instead, is an honest accounting of exactly how close 7 of humanity's most careful minds have actually gotten, and exactly where each of them stopped. The wall described at the very start of tonight is still standing exactly where it was found, unmoved by 7 decades of some of the most careful mathematics humanity has ever produced. That was never a failure hiding inside tonight's research. A wall that 3 independent theorems, 6 independent research programs, and a Nobel Prize's worth of physicists have all failed to walk around using completely unrelated tools isn't evidence of weak effort. It's evidence of how real the wall actually is. New instruments are already being built to press against it further. A space-based observatory called LISA, expected to launch within the next decade, will listen for gravitational waves at frequencies no instrument on Earth can hear. Waves some of tonight's proposals predict should still be echoing, faintly, from the moment everything started. It may finally settle the question bicep 2 raised and then lost to a cloud of galactic dust. It may simply open 3 new questions in its place instead. The wall was never a locked door. It was the shape of the room. The specific signal LISA is built to hunt for is called a stochastic gravitational wave background, not a single sharp chirp from one dramatic event, the way the first gravitational wave detections in 2015 caught 2 black holes spiraling into each other, but a faint, constant hiss spread across every direction of the sky at once, the kind of signal only an event as total as the beginning itself could have left behind. If tonight's inflation proposal is correct, that hiss should be sitting there, waiting, roughly at the frequency range LISA is being built to hear. If it isn't there when LISA finally listens, closely, for years, several of tonight's 7 proposals will need to be reconsidered from the ground up, and you will not need to have understood a word of the mathematics behind it for the result to still change something about how the sky looks the next time you're lying underneath it. Whatever LISA and its successors eventually find, resolution was never going to look like a single number appearing on a screen somewhere, settling the argument in an instant. It will look like what tonight already looked like. Careful people, in careful conversation with careful evidence, slowly ruling out what didn't survive contact with the universe, and slowly narrowing 7 proposals down toward however many turn out to still be standing in another 80 years. You will very likely not be alive to hear the final version of this particular program, if a final version ever airs. Neither will most of the physicists currently building LISA's mirrors and calibrating its lasers. That was never a reason not to care how it turns out. Every generation that has ever chased this question knew, going in, that the chasing was the part they'd actually get to keep. Most of the biggest questions a curious species has ever asked took centuries to close. And some of the best ones, this one included, may never close in anyone's lifetime, including the lifetimes of the physicists devoting theirs to it right now. That has never once made the asking a smaller act than the answering. Alfred Wegener proposed, in 1912, that the continents had once been joined together and slowly drifted apart. He was mocked by most of the geological establishment for decades. There was no known mechanism that could move something as massive as a continent, and without a mechanism, the idea looked more like a coastline coincidence than a theory. Wegener died in 1930 on a research expedition in Greenland. having never lived to see himself proven right. The mechanism, plate tectonics, wasn't confirmed until the 1960s, 3 decades after his death, once new instruments finally mapped the ocean floor well enough to find the spreading ridges his theory had required all along. None of tonight's 7 physicists know, right now, whether they are standing where Wegener stood in 1912, right and decades from being believed, or whether they are standing somewhere history will eventually file away as a beautifully argued dead end. Neither does anyone else. That uncertainty is not a flaw in tonight's research. It is the actual, ordinary texture of what it feels like to work on something before it's finished, which is the only way anything worth working on ever actually gets worked on. There is a particular kind of rest that only comes from setting something down without having finished it. Not defeat and not procrastination, just the ordinary decision every mind eventually has to make between continuing to turn a question over and allowing the body, finally, to stop. You get to make that decision now. The same way Wegener's colleagues eventually did. The same way every physicist chasing tonight's 7 proposals does at the end of every working day. Whether or not the equations on the page happen to resolve before they close their notebook. That is not a small kind of permission to receive at the end of a long night of unresolved physics. It might be the entire point of tonight having been built this way in the first place. 7 unfinished proposals, instead of 1 tidy answer, offered on purpose, to a listener who was only ever going to need permission, not resolution, before finally closing their eyes. You were not asked tonight to solve anything before you were allowed to rest. You were only asked to sit, for a while, next to 7 of the most careful attempts human beings have ever made at a question that may not have a bottom to find, and to notice that none of the not knowing made the universe any less yours, or this exact moment, right now, any less real for having arrived without an explanation attached to it. One last measurement before tonight's 7 proposals give way to sleep. It has nothing to do with how the universe began, and everything to do with the fact that you have been listening to all of it from a body that was never, for one instant, at rest. Earth turns on its axis at roughly 1,000 miles an hour at the latitude of most cities on this planet. That same Earth orbits the Sun at closer to 67,000 miles an hour, completing the full circuit once a year, correcting course by exactly nothing, needing no engine, running entirely on momentum inherited from a disk of gas and dust that existed before this planet did. The Sun, meanwhile, orbits the center of the Milky Way at something closer to 500,000 miles an hour, dragging Earth and every other planet in this solar system along with it, a trip so vast it takes around 230 million years to complete a single loop. None of those numbers is the strangest one. The Milky Way itself, the whole galaxy, every star in it, is being pulled, along with its neighboring galaxies, toward a region of space astronomers still argue about the exact cause of, nicknamed the Great Attractor, at something close to 1.5 million miles an hour. This isn't guesswork. It was measured directly in the cosmic microwave background this night kept returning to. The same ancient light carries a faint, lopsided warmth on one side of the sky and a faint coolness on the other, a dipole pattern that only makes sense if the entire galaxy carrying this exact room is barreling through space at a speed almost impossible to hold in the body. The same COBE satellite that first mapped the fluctuations behind every galaxy, discussed earlier tonight, also mapped this dipole with enough precision to turn it from a suspicion into a settled number. Later missions refined it further, but the basic shape of the measurement has held since the early 1990s. One side of the sky reads very slightly warmer, the other very slightly cooler, and the only explanation that fits every subsequent check is motion. This galaxy, and everything inside it, physically moving through the afterglow of its own beginning, every idea discussed tonight, every tunneling probability and inflating bubble and smoothed out pole, happened to something that has never once, in 13.8 billion years, held still. Stillness was never actually available to this universe. not for one single second of its entire history. And it was never available to the body listening to this either. Resting here tonight, moving through space in 4 directions at once, without feeling a single mile per hour of it. That, more than any equation heard tonight, might be the truest thing this night can leave with you. A body in motion since before it had a word for motion, still moving now, and moving for as long as it exists to keep doing it. Not a metaphor for how tonight felt, a measurement as real as any other number heard since the very start of tonight, sitting quietly underneath every breath taken while listening to it. Tonight, we drifted through 7 different mathematics, each one trying, in its own language, to answer a question that may not have a final answer at all, through tunneling probabilities and inflating bubbles, through a pole with no north and a far future disguised as a beginning, through colliding sheets of reality and a birth sealed behind an event horizon, through a landscape of possibilities too large for any single mind to hold. None of it was ever really about a universe out there, separate from you. Every proton in your body, every photon that has ever reached your eyes, every quiet, patient second of your own existence is made of the same unresolved argument tonight, spent hours sitting inside. You were never a visitor to this mystery. You are one of the places it lives. Walk, one more time, back through everything tonight covered, except forward. This time, instead of galaxies unclustering, watch them gather. Instead of stars going dark and folding back into gas, watch the first ones ignite, one at a time, out of the cooling plasma this night kept returning to. Instead of walking toward a wall neither physics nor tonight's questions could get past, walk away from it instead, into 13.8 billion years of everything that happened because, somehow, impossibly, undeniably, it did. All the way forward, to tonight, to this room, to whatever this night has been. If your eyes feel heavy, let them close. That was always where tonight was headed. If this felt like home, leave a comment when you wake up and tell this quiet universe where in the world you drifted off from tonight. If you're still here, still awake, still turning 7 proposals over in the dark, the next chapter is waiting, whenever you're ready for it. There is no wrong choice between the two. The universe will still be here when you wake up. So will we. Good night.